All right, welcome everybody. Today we're going to be talking about the difference between the old school Bohr model orbits and the new understanding of electrons as a wave in the quantum mechanical model of the atom, as they are actually waves. So we're going to make a connection between that Bohr model and this thing. So we've got our snake spring right here, and if we start putting waves on it and we get them at the most chill, and yeah, Marissa, you're doing great. You're just going to hold that real tight and strong. It's just like you're doing. It's perfect. And if we have the most chill kind of waveform we can have on here, we get this one loop going back and forth. All right, now this is the way that electrons actually exist around the atom. So if you take a look up on the board there, and Trinity, you can go ahead and show the board up there. All right, and you see the classic Bohr model with the red nucleus in the middle and the electrons in an orbit around it. We realize they don't actually orbit it like planets orbit the sun. They actually orbit it like this, with this spring here. This, just let it blur all together, it does make kind of a circle shape, right? So that's the true orbital. So we have this name that means orbit-y or orbit-ish. It's not an orbit, so we can't call it an orbit, but it's an area where you might find the electron waving, so it's called an orbital. It's orbitish. This is the lowest energy orbital we can have. Now, if you're like, hey, where is that electron? If the electron is represented by the actual, the particle of the electron is represented by this metal of this spring, so then you're like, well, where is the electron at any one moment in time? I want to find you, electron. Let me see where you are. Then you could take a picture, snap a shot, freeze frame it, and boom, you can see where this would be, frozen in a moment in time. But the picture is only one snapshot of where that electron was at that moment in time. You can't tell how fast it was moving from that still picture. Instead, you just kind of watch it like we're watching it now. Then you can tell if it's going slower or if it's going faster, right? You can tell its speed more. And so you get more of an idea of its speed by just watching it over time, or if you were to take one snapshot of time, you can tell where it was. This is what we call Heisenberg's Uncertainty Principle, where Werner Heisenberg said that an electron, you can know where it is, its position, or you can know its momentum, which is how fast it's going, but you cannot know both at the same time because they have to be measured differently. This is what we would call the ground state for our electron wave. Now, if I put in more energy, I can make an excited state for this electron wave. So right now my arm's pretty chill. Let's put in some more energy. And a zig, 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 zig.
Oh my god.
There we go. Boom!
There's two of them.
Yeah. So now you can see we got the two there going, right? This is an excited state. Notice my arm has to go faster. In fact, it actually works out pretty nicely. The math is twice as fast. And so we have two loops going. This is, we're not going to need three. but this is what we call a different shape for this orbital. This electron is now occupying the same space, but at a higher energy. And we actually have a different name for this shape. This is called a P shape. The other one was called an S shape. Now the S doesn't necessarily stand for sphere, but it kind of does make a sphere shape, right? If you let it just trace out its shape in 3D space. So you can remember S shape for sphere and lower energy. And then P shape, it's not really shaped like a P, it's more like a sideways 8, but we don't call it sideways 8 shape. We call it P shape. Thank you, Marissa. Let's give her a hand. Yeah.